Welcome back to the deep dive. Today, we're taking a step back from the big, high-level ideas and really zooming in on the blueprints, the absolute structural blueprints of computing.
Exactly. We're getting into the nuts and bolts of how data is actually
And
organized.
we're talking about a foundational building block, the linked list. Now, if you've only ever used standard arrays or, Python lists, this is a completely different philosophy. It's almost organic.
It is, and that's why we're doing this. The mission today is to really peel back those layers and get our heads around a singly linked list, sometimes called a forward list.
Right.
We want to grasp its unique features, its a very deep connection to recursion, and most importantly, the engineering trade-offs, what and why you'd actually choose this.
Okay, let's unpack this then. Let's start at the very beginning. Most of us think of a list as, well, a sequence, like books on a shelf,
Yeah.
right next to each other.
Contiguous.
Exactly. But the links list just flips that idea on its head. How is it even defined?
What's so amazing about it is its pure simplicity. It's actually defined recursively, which is a bit of a mind bender at first. A linked list can only be one of two things.
Okay.
First, it could be the empty list. Nothing. We usually represent that with a null value, like none.
Simple enough.
Or, and this is the absolute key, it is a single node that contains two things. First, the data itself, which we call the cargo.
The useful information.
The useful information, yes.
Right.
And second, a reference to another linked list.
Wait, so the definition of the thing contains the thing itself?
That's it. That's the recursive genius of it.
Yeah.
The structure is defined in terms of itself.
That immediately feels different. It suggests the whole collection is self-similar. But let's get a concrete visual. Tell me about that one building block, the node. What are the two non-negotiable parts inside it?
So the node class is designed to do just two things, but do them perfectly. First, you have that cargo field. It just holds whatever you want to store, a number, a name, anything.
And the second part is the magic.
That's the magic. It's the next field. And this field doesn't hold data. It holds a reference. You can think of it as a memory address, a pointer. It's the arrow that points to the very next node in the chain.
So if I'm picturing this, it's not a single block of memory. It's a bunch of separate boxes, maybe scattered all over, and each box just has a little arrow pointing to where the next one lives.
You've got it. They are logically sequential, but not physically contiguous. And to manage this whole chain, we only really need to know one thing,
The beginning.
the very beginning. The first node is called the head. That's your entry point. If you lose the address of the head, the entire list is just gone, lost in memory.
And I'm guessing there's a name for the other end of the line?
Of course. The last node is often called the tail. And its next field, crucially, has to point to that none value we talked about.
Ah, which satisfies the first part of the definition, the empty list.
Exactly. So to do anything with the entire collection, you just need that one single reference, that one pointer to the head. It's the root of everything.
Here's where it gets really interesting for me. The actual mechanics. If the nodes aren't side by side, you have to build that chain explicitly. So if I have node A, node B, and node C, I have to literally draw the arrows myself in the code.
Manually, yes. That's the fundamental difference. With an array, you ask for index 2, and the computer just calculates the address. Here, you have to create the relationships. You have to write the code that says node A.next now points to node B,
And then node B next points to C.
and C.next points to none. The whole structure's integrity hangs on those individual next pointers being correct.
And we keep coming back to that recursive definition. Why does that make linked lists and recursion such a natural pair?
Because you can look at any linked list, let's call it L, and you can always break it down into two pieces.
The head and now.
The rest, the head, the first node, and the tail, which is just another slightly smaller linked list. So the problem of, say, counting the nodes in L just becomes 1 plus the count of the nodes in the tail. The problem shrinks perfectly.
Can you give us a really concrete example of that in action? Because, recursion can feel a little abstract for a lot of people.
A classic one is printing a list backward. Now, if you try this with a normal loop, it's actually pretty messy. You'd have to go through the whole thing once, maybe store all the values, then print them in reverse.
Sounds clunky.
It is. But with recursion, the logic is, well, it's beautiful. You tell your function, okay, separate the list you were given into the head and the tail.
Right.
Now, before you do anything else, call yourself again on the tail. And only after that entire process is finished, all the way down to the end of the list, do you finally print the head's cargo.
Okay, hold on. So if I have nodes 1, 2, 3, the function gets to node 1 and says, hang on, I have to deal with the list 2, 3 first.
Precisely.
Then it gets to 2 and said, nope, wait, I have to deal with 3 first.
Yep.
And only when it hits the very end, node 3, which has no tail, does it actually print the 3. Then the waiting call for 2 can finally print, and then the original call for 1 prints.
You just explained it perfectly. You're using the computer's own memory, the call stack, to reverse the order for you. It's an unbelievably elegant solution that maps directly onto the structure of the data itself.
That really does deepen my appreciation for the structure, but it also raises the million-dollar question. If this is so elegant, why aren't we using linked lists for everything? What are the drawbacks?
And that is where the real engineering decisions come in. There are two major hits you take for choosing a linked list. The first one is access.
Access.
With an array, if you want the 500th element, you just ask for index 499. The computer does a quick calculation and jumps right there. It's instant. We call that O1, or constant time.
Okay. And with a linked list?
You have no choice. To get to the 500th element, you have to start at the head.
No.
Oh, yes. You follow the next pointer from the first node to the second, from the second to the third, 499 times.
So if I'm searching a really long list, a linked list is going to be painfully slow.
Painfully slow. Accessing the nth element is an ON operation. Linear time. The time it takes is directly proportional to the length of the list. It's like finding a word on a scroll versus using the index in a book.
That's a great analogy. Okay, what's the second big drawback?
Memory. It's overhead. In an array, your data is packed in tight. With a linked list, every single piece of cargo, no matter how small, has to carry that extra baggage. The next reference.
The pointer.
The pointer. Now, if you have a list with millions of small integers, the memory you're using just for the pointers could easily be bigger than the memory used for the actual data you care about.
So you're sacrificing memory efficiency for...
What?
What's the benefit that justifies slower access and a bigger memory footprint?
Structural flexibility. That's the superpower. Specifically inserting and deleting elements, especially in the middle of a very long list.
How so?
Think about an array with 1 million items. If you want to insert a new item at position 500,000, what does the computer have to do?
It has to shift everything down. Every single element from that point on has to be moved over one spot to make room.
Every single one. That's 500,000 elements being physically moved in memory. It's an incredibly expensive ON operation.
Right, because the whole second half of the array gets rewritten.
Exactly. But in a linked list, if you want to insert a new node after an existing one, the operation it's trivial.
What do?
You just change 2 pointers. You tell the previous node, hey, stop pointing to your old neighbor, point to this new node instead. And then you tell the new node, okay, you point to the one that used to be next. That's it.
You're just rewiring the arrows. The other 999,999 nodes are completely untouched.
Completely untouched. Insertion and deletion become constant time operations. O1. And that is a huge deal. It means the operation takes the same amount of time whether the list has 10 items or 10 billion.
So that's the trade-off. You trade fast access for lightning-fast modification.
That is the core trade-off.
But managing all those raw nodes, setting every single next pointer by hand, that seems really error-prone. Which I think brings us to this idea of the better approach from the source material, the wrapper class.
It's not just better, it's essential for any real-world use. The nodes themselves are just dumb containers. If you, the programmer, are manually manipulating them, it is so easy to make a catastrophic mistake.
Like what?
Like accidentally setting a node's next pointer back to an earlier node in the chain.
You'd create a loop, a literal infinite loop.
And your program will crash. Or worse, just hang forever. This is where the wrapper class, the linked list container, comes in. It's a layer of abstraction, a manager.
So what does the manager do?
The wrapper holds on to the really important metadata, like the reference to the head. And more importantly, it gives you a safe, clean set of methods to work with. A method to add an item, a method to delete an item, one to print the list.
So you, the user, never touch the raw pointers.
You never have to. When you call mylist.add new data, the wrapper class handles all the messy, delicate work of creating the node and safely rewiring those internal next references for you. It protects you from breaking the chain.
Okay, so this brings it all together. What does this wrapper idea mean for you, the learner, in a practical sense?
It's all about abstraction and reliability. You know, when you use a Python list and you call append, you don't think about how Python is reallocating memory under the hood. You just trust the interface.
Right.
A good linked list class gives you that same confidence. You get all these structural benefits, the fast insertions and deletions, without any of the dangers of managing raw pointers. The wrapper is the professional interface that guarantees the whole thing works.
And that brings us toward the end of our deep dive. So The core takeaway seems to be this. A linked list isn't just another kind of list. It's a fundamentally different, recursive, pointer-based structure that sacrifices access speed and memory efficiency for incredible flexibility when modifying its own sequence. It's a specialized tool for dynamic, ever-changing data. And we want to leave you with a little challenge, a thought experiment, that connects this structural knowledge to something very practical.
Okay.
We just talked about that linked list wrapper providing a print method. Now, a simple traversal just prints one item after another. But that's ugly. You want it to look nice, like 1, 2, 3, with brackets and commas.
But not a comma after the last number?
Exactly. So your challenge is this. How would you write the logic for that print method? How do you traverse the list of nodes but handle the formatting correctly? Specifically, making sure you don't print that trailing comma after the very last element.
That's a perfect little puzzle. It forces you to think not just about traversal, but about state and knowing when you're at the end of the line. Thank you for joining us on this deep dive into the very building blocks of data. Now go explore those references. We'll catch you next time.